All right, so let's get into a really cool piece of physics history. And I promise, this isn't just going to be a bunch of dry equations. Think of it more like a detective story. The mystery? A fundamental law of nature that was, well, broken. We're talking about the rules that govern particles like the electron. Back in the 1960s, physicists knew something was deeply wrong, and the story of how they fixed it is just incredible. It led to one of the most perfect theories we have. So yeah, it really all boils down to the single huge question. I mean, what do you do when a law of nature just stops working? When your whole understanding of the universe literally breaks down? Where do you even start looking for clues? To figure this out, we've got to go back to the scene of the crime and see exactly what was broken. All right, so let's set the scene. We're in the 1960s. Physicists have this theory for what they call the weak nuclear force. It's the force behind some types of radioactivity. And on the surface, it seemed okay. It kind of worked. But underneath, it was hiding a massive, fatal flaw. So the theory they were using, it wasn't just a little bit wrong. At low energies, sure, it did the job. But when you cranked up the energy, like in a particle accelerator, the whole thing just fell apart. The calculations would literally explode, giving you answers like infinity. And in physics, getting infinity as an answer is basically the universe screaming at you that your theory is broken. You've missed a huge piece of the puzzle. So, okay, the weak force theory was a total mess, a disaster. But the physicists weren't flying completely blind. They had a really important clue. See, they had another theory for a different force, electromagnetism. And that one, well, it was perfect. I mean, truly elegant. It worked no matter what you threw at it. So the big hope was, hey, maybe, just maybe, whatever magic ingredient makes electromagnetism so perfect is the exact same thing we need to fix this broken weak force. And what was that magic ingredient? That secret sauce? It turned out to be one of the deepest, most fundamental ideas in all of physics: symmetry. Now, when physicists talk about symmetry, they mean something really specific. Think about a perfect soccer ball. You can rotate it any way you want, and it still looks like the exact same soccer ball, right? That's a symmetry. And it turns out the beautiful theory of electromagnetism is built on a similar, but more abstract kind of symmetry. The idea is that the fundamental laws of physics don't change, even when you make certain changes to your mathematical description, and that was the clue they were looking for. Okay, but here's where it gets really interesting. Not all symmetries are created equal. The symmetry behind electromagnetism, which has the fancy name U1, is pretty simple. Imagine just a single pointer rotating around a circle. Easy enough. But the symmetry they started to suspect was behind the weak force, called SU2, that was a whole different beast. It was way more complex, more like a whole system of interconnected gears all turning and influencing each other. A much richer, more powerful kind of symmetry. And this is where the idea gets truly mind-bending. This more complex SU2 symmetry suggested something wild. It said that particles we thought were totally separate, like the electron and the much lighter, ghost-like neutrino, weren't separate at all. They were actually just two different states of the same underlying object. It's like you could rotate an electron and it would turn into a neutrino. This was huge. It wasn't just about fixing a broken force, it was about finding a deeper connection between the building blocks of matter itself. So, this symmetry idea was beautiful, it was elegant, and it was about to hit a brick wall. A really, really big one. Because it made a very specific prediction that just flat out contradicted what we knew about the real world. You see, there was a fatal flaw. Any theory built on this kind of perfect symmetry came with one unbreakable rule. It predicted that the particles carrying the force, the little messengers, must have zero mass. Absolutely massless. No ifs, ands, or buts. Now for electromagnetism, that's perfect. Its messenger particle, the photon, is massless. That's why light can travel across the entire universe. But the weak force? I mean, the clue is in the name. It's incredibly short-ranged. It only works over teeny-tiny distances inside an atom's nucleus. And for a force to have such a short range, its carrier particles have to be super heavy. So you've got this beautiful theory screaming massless, while reality is screaming massive. It was a complete contradiction. The whole gorgeous idea looked like it was totally dead in the water. But just when it seemed like all hope was lost, a breakthrough came from a totally unexpected direction. It wasn't a fix, it was more like a loophole. A clever, ingenious way to have your cake and eat it too. This new idea, which we now call the Higgs mechanism, was brilliant. It said, what if the underlying laws of nature are perfectly symmetrical, but the universe we live in is not? Imagine a perfectly balanced pencil standing on its tip. That state is symmetrical. But it's unstable, it's gonna fall. When it falls, it picks a random direction, and that beautiful symmetry is broken. Or rather, it's hidden. The idea was that a similar thing happened to the entire universe. An invisible energy field, the Higgs field, froze the universe into one particular state, hiding the perfect symmetry and, in the process, giving mass to particles that pass through it. And this is where a physicist named Steven Weinberg had an absolute stroke of genius in 1967. He realized you could take all these puzzle pieces and fit them together. He took that complex SU2 symmetry for the weak force, combined it with the simple U1 symmetry for electromagnetism, and then he applied this new hidden symmetry trick. And when he did, boom, everything clicked into place. The weak force and electromagnetism weren't two different forces anymore. They were just two different aspects of a single, unified electroweak force. And the best part? The theory made these incredibly precise predictions. Once the math for the hidden symmetry played out, what did we get? Well, the photon, the messenger for electromagnetism, popped out completely massless. Perfect. Check. But then 3 other force carriers also emerged. The W+, the W-, and a brand new one called the Z0. And they all came out of the equations with massive amounts of, well, mass. They were exactly the heavy particles the weak force needed. It just worked. You know, this is the sign of a really, truly great theory. It doesn't just clean up old messes. It makes brand new predictions about things no one's ever seen before. And Weinberg's model did just that. It predicted that this new Z particle would allow for a whole new type of weak force interaction, something called a neutral current. Nobody had ever seen anything like it. So now the theory had put its neck on the line. It was time to go out and see if it was right. Now, you'd think everyone would have jumped on this brilliant idea, right? But actually, Weinberg's paper was mostly ignored for a few years. The math was just monstrously complicated, and nobody was even sure if it was truly consistent, if it secretly had those nasty infinities hiding somewhere. But eventually, the moment of truth arrived. I just love this quote because it captures the pure human excitement of scientific discovery. Abdus Salam was another physicist who had worked on these ideas. Imagine just being stopped on the street and hearing this from a colleague. Get into the car, I have news for you. We have found neutral currents. Just like that. An experiment at CERN had seen them. The crazy new prediction made by the theory, it was real. It actually existed. And that discovery was really the final nail in the coffin for any doubt. The whole thing came together in just a few years. In 1971, this brilliant physicist, Gerard 't Hooft, proved that the theory was mathematically solid. He showed those infinities were gone for good. And then, just 2 years later in '73, came that experimental discovery at CERN. Suddenly, this ignored idea went from a weird, speculative paper to an absolutely essential cornerstone of modern physics. And just like that, our detective story comes to a close. What started as a hunt for a fix to a broken, messy theory ended with something so much bigger. It ended with a truly beautiful, unified picture of how the universe works. The weak force and electromagnetism, two things that seem so different, were finally shown to be two sides of the same coin. It was a giant leap forward in seeing the deep unity of everything. This amazing success story just begs one final, massive question, doesn't it? We managed to unify 2 of the 4 fundamental forces of nature. So what about the other 2? What about the strong nuclear force that holds atoms together? And what about gravity? The quest to find that one final, perfect theory that joins them all, well, that's a story that's still being written.